The prediction of the molecular geometry of the xenon hexoxide ion using the VSEPR theory, valence shell electron pair repulsion theory. We draw the Lewis structure first. Xenon, the central atom, is found in the 8th group and 5th period of the periodic table. It is a noble gas and has already got 8 valence electrons around the nucleus. Xenon, though, has got d orbitals. Having d orbitals, it can form the expanded octet. The oxygen atom is found in the 6th group and 2nd period of the periodic table. It has got 6 valence electrons that can be used for covalent bond formation. The ion will accommodate 4 extra electrons. These electrons will be located on the more electronegative atom oxygen, so that we have got 4 oxygen atoms with 7 valence electrons and 2 oxygen atoms with 6 valence electrons. Central atom xenon, 8 valence electrons. 2 oxygen atoms having 6 valence electrons. 4 oxygen atoms having 7 valence electrons. We make use of a large bracket to indicate the charge on the molecule. As a first suggestion, we can suggest a dative covalent bond to form from the xenon to the oxygen with 6 electrons. The xenon atom will donate 2 electrons to an open orbital around the oxygen atom. Looking at the other bonds, we form the ordinary covalent bond where 1 electron is donated from the central atom and 1 electron is donated from a terminal atom. When the central atom has got d orbitals and we want to predict a molecular geometry that will compare better with the geometry measured in the laboratory, we change the dative covalent or coordinate covalent bond to a double bond, so that a better suggestion for a Lewis structure will be the central atom xenon bonded with a double bond to this oxygen, bonded with a double bond to the oxygen, and single bonds for the other 4 oxygen atoms. We've introduced 2 double bonds, but the correct structure of this molecule can be better described when we use resonance structures. The choice was to introduce the double bonds in these positions, but the double bonds can also be introduced either in these 2 positions or in this position here, that position there. So we make use of so-called resonance structures to describe the molecular geometry. Per choice now we make a double bond in this position here, double bond to this oxygen here, and then single bonds to the other 4 oxygen atoms. And we can continue writing resonance structures for this molecule. The average of all the resonance structures will represent the molecule. All the bonds will have the same nature. They will not have single bond or double bond character. The nature will be something in between. There is just one correct molecular geometry for the molecule. And when we look at possible distortions, we see that first, xenon hasn't got any lone pairs, but secondly, we haven't got either double or single bonds. We have got bonds that's exactly equivalent, and these bond angles then will not be distorted. We've got a central atom A bonded to 6 terminal atoms. For the molecular geometry, we first need to look at the electron pair geometry AB6. AB6 electron pair geometry will predict the octahedral geometry. The bond angles all equivalent, exactly 90 degrees. We predict for our molecular geometry an octahedral structure with no bond angle distortions, bond angles all 90 degrees. We make use of Cooper or Cowper structures to draw the molecular geometry. Central atom xenon, double bonded oxygens, single bonded oxygen atoms. Although we introduce the lone pairs on the terminal atoms, realizing that the lone pairs will not influence molecular geometry. Only lone pairs on the central atom will influence molecular geometry. We must indicate, though, that we can write several resonance structures for this molecule. And we can write even more resonance structures. The molecular geometry is then octahedral. Bond angles all equivalent, no distortions. Because we haven't got a double bond in this position, we have got something in between a double and a single bond. When we look at the molecule, we must realize that the molecular geometry will depend on the positions of the atomic nuclei in three-dimensional space. We've got the central atom xenon here, 6 terminal oxygen atoms. In this instance, we have got bonds, something of a single bond and something of a double bond character here. Not pure single, not pure double bond character, but they are all exactly the same. Bond angles will not be distorted, all the bond angles 90 degrees.